Okay, so today we're going to be talking about geometric sequences. And I want to show you first about how does an arithmetic and a geometric sequence differ. So if you take a look at this example, you're starting with a ball that is dropped from a height of 10 feet. Each time it rebounds, it comes to a height that's 60% of its previous height. Just so you're aware, to get 60% of something, multiply 0.6 times that and you'll get 60%. So as you take a look at the heights after each rebound, let's think about, does this make an arithmetic sequence? Remember, an arithmetic sequence was special because you had a common difference. If you subtracted any two consecutive terms, it came out to be the same difference. You notice in this case, it's not. Okay, if I do 10 to 6, that's a difference of -4. But I'm definitely not subtracting -4 to go from 6 to 3.6. If you even think about the way that I just mentioned how I constructed this before, I'm constantly multiplying by 0.6. And the fact that I'm multiplying by a constant growth factor, that should sound familiar to you, is the reason why this is not an arithmetic sequence. It's actually exponential. Okay? And the growth factor is that 0.6. So hopefully that reminds you of when we did exponential functions, the fact that this is less than 1, this is something that is decay. You can see right here in the table, as we go down the table, the values are getting smaller. That's just to connect back to stuff that we had talked about before. So here comes the important stuff with how do you identify a geometric sequence? How do you make a rule for it? Just like we made a rule for the arithmetic sequence, you can also make a rule for a geometric sequence. The biggest difference now that we're dealing with geometric sequences is we're looking for a common ratio. Okay, that common ratio is always going to come from taking the second term, and instead of subtracting the first term, you're going to divide by the first term. So our common ratio is going to come from doing 6 divided by 3. You see that comes out to be 2. Or 12 divided by 6, that comes out to be 2. Or 24 divided by 12, that comes out to be 2. That's our common ratio in this case, is 2. Okay? So the common ratio equals 2. To write an expression to represent a geometric sequence, this is how you do it. A sub n, so I'm still looking for the nth term, equals a1. I'm still starting with the first term. The only difference now is that instead of adding a common difference, I'm multiplying by a common ratio, and when you multiply something over and over again, that's what creates an exponent, so I'm raising this to the n minus 1 power this time. Okay, so again, you're going to want to make sure you keep this in mind, because as we go through this lesson, you're going to use this formula a bunch of times. This is the formula to create a geometric sequence. Okay, so how do I make this rule for this geometric sequence? A sub n is our nth term, again, our general rule. Our very first term, a1, had been 3. We're multiplying by a common ratio of 2. And the fact that I keep multiplying by 2 over and over, that's why my common ratio is raised to the n minus 1 power. That's the explicit formula, and that's the one that I can use if I want to find the 20th term without sitting there and multiplying by 2 and multiplying by 2 over and over again. So just like we did in yesterday's lesson, you first want to be able to identify if something is geometric or not, and then if it is geometric, let's make a rule for it. If you look at the first one, you're adding by 5 over and over and over again. That is not geometric, that is actually arithmetic, and has a common difference of 5. If you take a look at question number 2, you're timesing by 3 over and over again. So the fact that you're multiplying by a common ratio over and over and over again, that's what makes this a geometric sequence. It's okay for a geometric sequence to be have a common ratio. That is a fraction. So if you take a look at number 3, don't think of it as dividing by 2 and dividing by 2. Think of it more as multiplying by 1/2 and multiplying by 1/2. Remember how I mentioned finding the common ratio above? What did I do in each of these? I took the second term and divided by the first term, or the third term and divided by the second term. So if I take the second term and divide by the first term, you can see that that comes out to be a common ratio of 1/2, and that's why I have a common ratio of 1/2, and that is also why this is a geometric sequence. Okay, this last one is neither. This one does not arithmetic or not geometric. There's no common difference or common ratio. Okay. So if you skip ahead to question number 7, as I've mentioned before, the reason why you'd want to be able to make a rule for a geometric sequence is to be able to find a specific term of that sequence. So if you take a look at question number 7, you can see that you're constantly multiplying by 5 over and over again. We have a first term of 1. So if I make my nth term rule, a sub n equals a1r to the n minus 1, a sub n is equal to 1 times 5 raised to the n minus 1. Now, even though I know that my first term here was 1, I want to make it very clear you are never to multiply these two terms together. You need to think about order of operations. Order of operations says you must complete an exponent before you multiply by what's in front. So absolutely under no cases are you ever to multiply these together. Okay, you leave it as 1 times 5 to the n minus 1, or in this case, you could also actually have left it as just 5 to the n minus 1. Okay, so take a look at the next one. As I go from 20 to 100 to 50 to 25, I'm constantly multiplying by 1/2. So my common ratio is 1/2. So a sub n is equal to a1, which is 200, times 1/2 raised to the n minus 1. Okay, so now in this first case, I wanted to find the 8th term. I apologize, I didn't do that earlier. That means you want to again plug in n equals 8. So I'm going to take the rule we just found, a sub 8 equals 5 to the 8 minus 1. In other words, I'm basically doing 5 to the 7th power, and you can see that that's pretty large, right? 5 to the 7th power. And so that comes out to be 78,125. Huge, right? You're just going to the 8th term, and it's already at 78,000 when it started at 1. That's something interesting about geometric sequences that you didn't see with arithmetic. These get really big really fast. Or if you take a look at the next one, you're doing 200 times 1/2 to the n minus 1 and plugging in n equals 11 this time. So when I find the 11th term, 200 times 1/2 to the 11 minus 1 comes out to be 25 over 128. Okay, you'll see this came out to be a pretty small decimal. You'll notice these functions get really big really fast or really small really fast. And what does that sort of sound like? Sounds like exponential functions. That's what you would see if you actually took this sequence from problem 6 and put this on a grid. If you actually started plotting some of the points, you would end up seeing that it starts with something like 110, and then 110, and then 2 is basically like 3, and eventually you end up seeing something that comes to look like that. Once again, you notice I'm not going to connect these points. That's the one thing that's always different between a function and a sequence, is the fact that these are discrete points as opposed to connecting them with an actual function. But I will point out that this is really important, what you just found out, is that geometric sequences, are exponential functions. Okay? So again, that's why they get really big really fast or really small really fast, depending on what your growth factor is like. Once again, the biggest difference is that the domain for a geometric sequence is that it's only positive whole numbers, whereas for an exponential function, it normally would have been all real numbers. Okay, you're only plugging these whole values. Okay, so that's again the biggest thing I want you to get out of that. Geometric sequences are really exponential functions. So I just want to do a little bit of practice with using some of the other given information to be able to find out what's happening with this sequence. So it says, given a term of the sequence and the common ratio, write an explicit definition for the nth term and find the first 3 terms. I'm just going to find an explicit definition. That's really what I want to see here. So if you remember, as I just mentioned, for a geometric sequence, our rule is a sub n equals a1r to the n minus 1. Okay, so if you take a look at this rule one right here, this is telling you that when n equals 4, a sub n equals 25. And we also have that the common ratio is -5. So watch me plug in. So a sub n is equal to 25. a1 I don't know. I'm going to have to work backwards to solve that. R is -5. And that's being raised to the 4 minus 1, or really being raised to the 3rd. So if I start to simplify this, I find out this is a1 being multiplied by -125, because it comes out to be -5 to the 3rd. And when I divide both sides by -125, I end up getting -1/5 for the value of my a1, and that gives me a final answer of a sub n equals -1/5 times my common ratio of -5 raised to the n minus 1.